Hello, everyone. You can hear me?
Yes, sir.
So,
All right, perfect. Okay, so let me share my screen first. Okay, so the plan for today is really to solve some of the past paper questions from the chapter of gravity, right? But before we do that, is there any question from the last lecture?
no, sir.
All right, so no question from anyone? Hasib and Omar, no question?
No, sir.
Sir, I haven't gone through the topic really well. So once I go through, I will ask tomorrow.
Oh, okay. So that's completely okay as well. Okay, so we'll be solving these questions, and we'll do them in a way. We'll make it a bit interactive, right? So we'll read the question, and I'll ask you your opinion about the question. How would you think? How should we go about it? And then according to that, we'll solve it really together. So it doesn't matter. I would also like to point out at this point that it really doesn't matter if you don't get the answer right, even if your answer is wrong. It doesn't matter. The one of the purposes of this thing is also to build your confidence to basically answer the problem, right? To think. The main idea is to motivate you to think about the problem. So it doesn't matter if you get to a wrong conclusion. Just think about it and present your ideas. So it will be more like a volunteer. So you can volunteer to answer the question. If nobody chooses to volunteer, then I guess I'll have to point out using your names. But you don't have to be scared or anything. Of course, it doesn't matter if you don't get how you should do it. You can just say that you don't really understand it at this point. But the idea is to make you think about the problem, right? So so far from whatever we have studied in gravity, here we have the first question, question 1, and that says define gravitational field strength. It's really just a definition. Does anyone in the class remember how did we define gravitational field strength?
Measure of force of gravity.
Yeah, you can really say something like that, yes. So measure of force of gravity on a mass, right? So yeah, so it's really defined something as at a point it is just the gravitational force, right? And it is acting, this force acts on a mass, right? So it is the gravitational force acting per unit mass. So it's really just G is equal to F over M, right? Where this F is the force of gravity. It was the force of gravity was just capital G M over R squared. And if I divide this expression, if I want to find G from this, I'll just divide it by the mass. So the only part that remains is the capital mass, which is the mass which is more majorly responsible for this gravitational field, right? So that's how the gravitational field strength is defined. So that was a pretty simple, just 1 mark question as well. Is there anyone who has any problem with this?
Sir, won't we write negative gm by r square?
Oh, yes. So that's a very good question. It depends how you are, how are you writing down your force, right? So if I say that this is a vector quantity, if I'm writing it as a vector, then you add this negative sign over here. Sometimes what you can also do is you can write it as a vector and you can add a vector symbol on R and then square it like this. Then also you'll not include the minus sign because that negative sign is a part of that vector. But if I'm just writing the magnitude of R square over here, and over here I'm saying that F is a vector, then I have to include that negative sign, which is going to tell me that the force of gravity vector points in the opposite direction as R. But if I'm not considering F, I'm just taking that, let's just take the absolute value of F, then I don't really need this vector. I'm just you're just considering the magnitude of F, right? So then you will not use that minus sign. So is that clear?
Yes.
All right. Okay, amazing. So no more questions from this part A.
No, sir.
Okay, I guess not. So let's move to this part B. We have this thing. A spherical planet has a diameter, this thing, 1.2 times 10 raised to power 4 kilometers, and the gravitational field strength at the surface of the planet is also defined. So we have the diameter from which we can get the radius, right? Because it's just radius divided by 2. Sorry, it's 2 times radius, right? Diameter is just 2 times radius, so you want radius, so you'll just divide the diameter by 2. Gravitational field strength, which means G, is also given. It's 8.6 newtons per kilograms. Wonderful. So the planet may be assumed to be an isolated in space. So it's isolated in space. So it is just alone in space. It's really free from any other forces in space. And to have its mass concentrated at its center. So it's just this thing that we always, whenever we do calculations, we consider things to be point masses, right? Anyone has any idea why is that so? Why do we consider things as point mass? So for example, if I have a planet, the planet there, I could consider this part that has its own mass, but the entire planet, I consider this planet we can take and we can say that it's just a point, and this point has some mass, right? So it's a point mass. Why do we do that? Does anyone know?
Is it because it will be difficult to individually use all the particles?
Exactly. So that's exactly the reason. So when you consider, for example, let me give you an example of a person. We even treat a whole person as a point mass, which is kind of funny, at least to me. But you can take this whole person and you can reduce him to the point mass and say that this point mass now weighs, for example, 70 kilograms. Now we do that because we can say that this point mass is really, what point is that? If I compare it to the person, it is the center of mass of the person, right? So the center of mass of this person is where we can assume that all of the mass is concentrated at that point, really. So instead of saying that this leg weighs something, it has a mass, this leg has a mass, this hand, these two hands, arms, they have some mass as well, right? So instead of doing all those and seeing what forces are acting individually on these things, it makes the problem very difficult. It turns out that you can treat this whole thing as a point mass and still get correct answers. So why not make our lives easier, right? So we just treat things as point masses. So just a piece of information over there. And we are required to calculate the mass of the planet. So again, we know the diameter of the planet, and we are given that the planet is spherical in nature. and in geometry basically, and the acceleration due to gravity is also provided. So any volunteer who would tell me how do I go about this problem?
Will we use the formula G is equal to a universal gravitational constant over R
Yeah,
GM
okay.
over R square?
Yeah. Over R squared, right? Exactly, right? So because we are provided with this thing, we are provided with this well, we are really provided with D, so I'll admit that we are provided with R, and G is just a constant, so we can just rearrange this expression to find M, and so M is really G R squared divided by the universal gravitational constant. So just find out the radius. So okay, I don't have a calculator with me at this point, but that's just a matter of putting the values, right? So we'll just put the values in place of sorry, can you repeat what are you saying?
Radius is 6,000.
Yeah, radius would be 6,000. It's in kilometers, so you have to remember this thing, right? So when I use these values, so if I'm using acceleration due to gravity as well, it's given, right? So this is not planet Earth, you have to remember that. So it's 8.6 newtons per kg, right? Sorry, newtons per kg. Now newtons is what? It is kilograms meters per second squared, right? So I'll have to convert the radius from kilometers to meters, right? I cannot just use this value, right? Okay, so that was one of the main points really. So in place of R, I'll put 6. Okay, so you'll have 6. It would be 6,000 kilometers, right?
Yes, so it is 6 million meters.
Yes, so you'll just add 3 more zeros to it to get rid of this k, right? So that's just multiplying it with 1,000. We're just putting the value of k, and then we have meters, and then you'll just divide this whole thing. Of course, you'll square it, and then you'll just divide it by whatever this value is. I don't really remember. I think it's 6.67 into 10 raised to power minus 11, maybe.
Yes.
Right? So you'll just put in these values, and it will give you a value for mass. And so only in this case, when you keep track of your units, you will get the mass in kilograms, right? So now it's just a matter of putting in the values and just calculating. So any problem in this part of the question? By the way, also, is everyone okay with this fact that I'm not really doing this whole thing of putting in the values and calculating the answer and then writing it down over here? That's just I think it's just a waste of time, as we all know how to use a calculator, right? Calculate and then write down the answer. The main idea is just to get the method across, right? The concept and the way of thinking of how to go about a problem. So is that cool with everyone?
Yes.
All right.
Yes,
perfect.
sir.
Okay, so is there any question at this point from anyone?
No.
No questions.
No.
Okay. Okay, good. So then we can move on to the next part, which says that, okay, so the gravitational potential at some point X above the surface of a planet, the planet, he's talking about the planet that we just solved for in B part, is minus 5.3 times 10 raised to power 7 joules per kilograms. For point Y above the surface of the planet, the gravitational potential is this thing. So really we have a planet, and there are 2 points above the surface of this planet. I'm not going to label them at this point as X or Y, because to read the question, we have to tell with a reason whether point X or point Y is near to the planet. So have a look at this question, and anyone who is volunteering to give an answer for this thing.
Y is nearer.
Y is nearer. Okay, so your reasoning behind this thing.
Because as we go above, the gravitational potential will decrease.
Yes, exactly. As you go above the, because we have this thing, right? As you go,
But
you're
sir,
saying as we go above. Okay,
as
so
we go
think
above,
in terms.
the decreases, but right here it is negative. So like minus 6.8 is
Exactly,
less
because exactly. So you know that the potential is defined as well, really, as the is proportional to negative of 1 over r, right? So the potential is really decreasing when the distance from the planet, this vector, is smaller, right? So whatever point that has a less potential would be closer to the planet, right? So minus 6.8, this value is smaller compared to this value. Everyone agrees with that, right? So it's, I mean, it's just -2, -1, 0, 1, 2. So which is smaller? -2 is smaller than all of these values, right? So just that concept. So minus 6.8 is smaller than minus 5.3. Both have a factor of 10 raised to power 7. So we can just ignore that when we're comparing these two values. So is that clear for everyone?
Sir, can you explain it one more time?
Yes, of course. So basically this is the potential, right? So potential phi is really varies inversely with a negative of r. So how did I say this? Well, we know that the potential is defined as minus gm by r, right? That's the expression for the gravitational potential. Now remember that there is this negative sign over here, and this thing is really telling you that when the potential will be smaller, or we can say in terms of the radius, when the radius or the distance of any point in space would be smaller, or it would be closer to the surface of the earth, in that case the potential would decrease, right?
Sir, why would it decrease?
Okay, so well, if you think in terms of this expression, phi is proportional to -1 over r.
I get it,
So
sir. I get it.
So yeah, so if you're going away from the planet, the potential is really increasing because there is this negative sign as well. If there was this negative sign was not over here, then the story would be different, right? So that's understandable.
Yes, sir. Yes.
Okay, perfect, good. So that's what I'm really promoting at this point, thinking, right? So okay, so this means because of this thing, we would say that point y is closer or nearer to the surface of the earth. So is this clear for everyone? And not really earth, I keep saying earth, but this is just some random planet. So is that clear for everyone?
yes.
Okay, amazing.
Yes, sir.
Good. So we can move on to this question now. Same question, different part. A rock falls radially from rest towards the planet from one point to the other. Calculate the speed of the rock. So there is a planet and the rock is falling radially. Radially means just in a straight line. towards the planet, right? So it falls from, you can say that it falls from this point. These 2 points are really X and Y, right? So let's say he's saying that it's falling from one point to this point. So we have already established that the point closer to the Earth is Y, and the point, that means the further away point would be X. So is this clear? The statement of the question is clear?
Yes.
Okay, so we are required to calculate the final speed of the rock. Now, think in terms of energies, because if something is falling, which energy is being converted to what energy?
Gravitational potential to kinetic.
Yeah, so gravitational potential energy is being, well, we can write it like this. I use this symbol V for any type of potential and T for kinetic. Would everyone be okay with that? I guess let's just use KE for kinetic and just PE for potential energy. Okay, so that's what's happening. So now how would I use the information that I have, which is in terms of potentials, right? So I have potentials at point X and I have potential at point Y. So these are the two potentials that I have. And now we also have this knowledge that potential energy is being converted into kinetic energy. So how will I use these two things to calculate this final speed of the rock with which it approaches this point Y? Anyone who's willing to? Again, think in terms of energies, right? The conservation, or really the conservation of energy.
So what was the question, sir?
Yeah, so the question is that you have a rock which starts its journey from point X and it's falling towards point Y. That's what it says in the question. A rock falls radially from rest towards the planet from one point to the other. Now, obviously, if it's falling, it would fall toward, and they told you it's falling towards the planet. So it's falling from the point that is further away to the point that's closer. We have already established that Y is closer to the surface of the Earth, which means that X is the point that is farther away from the surface. So the rock, when falls, it would start its journey from point X and it is going towards point Y, according to the question. So we need to compute the final speed of the rock, and that final speed will really be the speed with which it approaches this point Y, this one. So we need to compute that speed. Thinking in terms of energies, how would you solve the problem? Any clue, any suggestion?
The change in potential energy will be equal to the kinetic.
Yeah, exactly, right? So you would use this idea that the change in the potential energy will be the gain in the kinetic energy of this rock. But now when you're doing this, you'll write it something as mg, and the change in, let's say, change in some height, right? Or you can also write it in terms of this thing gm by r, right? Minus gm by r minus gm by r. And then you can, what do you have over here? Is equal to the kinetic energy, which is half mv squared. But the problem is about what do we do about this mass? We don't know the mass of the rock, right? So we really do not use, we don't go into this form of the potential energy. We'll not go into its expression. We'll remember that gravitational potential and how the gravitational potential was related to gravitational potential energy. It was related in this way that the potential energy was simply the mass times this gravitational potential. That's what we saw, right? Before in the in the last lecture, really. So I can just get rid of this mass. If I can get rid of this half mv squared on the right hand side, it's kinetic energy. So I can get rid of these masses, which leaves me with the fact that the change in potential is really equal to half v squared, right? So the mass is eliminated from both sides. So is that clear?
Yes.
Okay, good.
Sir,
Yeah.
sir, what would be right instead of the change in potential? Like for
Half mv squared, right? So it's really mg change in height is equal to and we're just getting rid of these mass m, and now we can just use this thing is just the potential, right? Change in potential, and on the right hand side we have half v squared. Now we can just factor out this v, and we know both the potentials. We know the potentials at point x, and we know the potential at point y, right? These two potentials. So we'll just put these values in. So we'll really have, let me do it on this side. We'll really have this thing that it would be 6.8 minus 5.3 into 10 raised to power 7. And this is equal to half and v squared. So v squared is really 2 times 6.8 minus 5.3 into 10 raised to power 7 square root. Sorry, if I get rid of the square, then this would be just square root, right? So is that clear for everyone?
yes, sir.
Okay, clear for everyone? The rest of the students as well?
Yes.
Okay, perfect. So that's this. And okay, so before we start this next one, is everyone who is in the class at this point, are you all enrolled in the course?
Yes.
Yes, sir.
Okay. Okay, so we have Alicia, Anna, Hasib, and Umar. Okay, Umar, I think you're enrolled, right?
Yes, sir. I'm enrolled.
Okay. How about Hasib? Are you enrolled as well?
Yes, sir.
Okay, you're enrolled as well. I'm sorry, just give me a second. Let me have this thing. Okay. And how about Anna?
Yes, sir.
You're enrolled in the course?
Yes, sir.
Okay, so and so is Alicia. Alicia, you're also enrolled?
Yeah.
Okay, so you all of you have basically paid the tuition fee, I think they call it. I'm not really sure. All of you have paid for the course? We have Hasib, Umar. Okay, so yes, all of you have paid for the course, or is it still pending for anyone?
Paid, sir.
Okay, that was Umar.
Yes.
Okay. Okay, so Hasib, Anna, and Alicia, you have also paid, or it's pending at this point?
Yes, sir. It's paid.
Okay. Okay, so there's okay. All right. Okay, so let's start this next question. we have this thing. By considering the gravitational field strength at the surface of the Earth, show that the mass of the Earth is this thing. So they have already given you a hint basically in this question that you have to consider the gravitational field strength at the surface of the Earth, and you have to find the mass. So, well, it's really easy, right? What do I do? We know that the gravitational field strength at the surface of the Earth is around about 9.81 meters per second. And I'm required to find out the mass, right? So that's what I want to find out. So anyone? Radius of the Earth is also known. It's it's really 6,000 kilometers. It's actually 6,400, or it's 638. You can say 6.38 into 10 raised to power 6 meters, right? In meters. So of course we'll just use this thing, right? G is equal to
Gm over r squared.
Gm over r squared, exactly. Now it's just a matter of putting your values. You'll just write this expression for mass, which would be g r squared over g, and it's the same thing as we did previously. And if you put in the values of g and r, 0.81 meters per second are in this thing. The only thing at this point is that you should always remember to check or to make sure that your units are agreeing with each other, right? The rest of the question is very simple. So once you do that, you put in the value of the gravitational constant G, and you can find that the mass is really 5.99 into 10 raised to power 24 kilograms. So
Sir,
no questions. Yeah.
when in the question,
Sorry,
how is
can
the
you repeat?
formula is R given in the formula sheet?
The radius of the Earth, it's normally given in the formula sheet. Yeah, as far as I can remember, it's given in the formula sheet. Yeah.
Okay.
Okay. So you can just remember R as even if you remember it as 6,000 kilometers, it's quite well enough. Even if I'm just saying, even if you're, for example, not given, or it's just easy to remember. It's a very what can you say? Easy to remember value, right? Or you can just remember 6,400 kilometers. Both of these really kind of work when you're solving a problem. So anyways, but as far as I can remember, yeah, it's given in the formula sheet as well. Here as well, right? I don't think there would be any questions. It's the same thing that we did before as well. Right? No questions? Okay. So here we have a next problem, and it says that the global positioning system, which is really a GPS, is a navigation system that can be used anywhere on the Earth. It uses a number of satellites that orbit the Earth in a circular orbit at the distance this much above the surface of the Earth, right? So you have to remember this distance is above the surface of the Earth. So this is Earth, and let's say here we have a GPS satellite, and the distance from this surface of the Earth to this is 2.22 kilometers. Well, 10 raised to power 4 kilometers. Right? And the center, from the center of the Earth to the surface, that's just the radius, right? 6,400 kilometers. Now, use the data from the previous part A to calculate the angular speed of this GPS satellite. So we need to find the angular speed of the satellite using information from, well, here, right? So the information that we'll be using is the mass of the Earth. Any idea, by the way, how do I solve this problem? We need to compute the angular speed of a satellite, right? And we are given the distance of this satellite from the surface of the Earth as well. And we are given a very strong hint, I might suggest at this point, is this one, circular orbits. So any clue, any idea, how should I tackle this problem? Anyone?
Then which the radius would be added up together?
Well, not really. We'll not add the radius, but think in terms of the forces that would be on this satellite. The force on this satellite is the gravitational pull, you can say, towards the Earth, right? So it would be the force of gravity that is attracting this Earth. And the resultant of that force of gravity is the centripetal force on the satellite, right? So it's the force of gravity really which is keeping this satellite in this orbit around the Earth, right? So which really means is that these two expressions, I can really equate the force of gravity to the centripetal force, as it is force of gravity is responsible for the centripetal force here. But I know that the force of gravity is really gm by r, what is it, r squared, right? And the centripetal force, I need to compute angular speed. So I know the expression for centripetal force in terms of angular speed. And what was it? It was mr omega squared. Does anyone remember?
It was mv squared by r.
Okay, yes, you're right. It was mv squared by r. And from this, I can write in v in terms of omega, because v is r. You can say r omega. So this becomes m r squared omega squared over r. This goes with this, and we're left with m r omega squared. So that's the centripetal force, right? And so this means that this is mr omega squared. You can use, we're using a capital R, so just use a capital R.
So we have to find omega or angular.
Omega is the angular speed, right? This one is known as the angular speed, while v is just the translational or the linear speed. So omega is a speed with which it moves in this circular orbit, and v is that speed at any point. It's a tangent to that point